Yes, and I'll share my screen as well. All right. Okay, can you see my screen?
Yes, we do.
All right.
At least I can, yeah.
Okay, so but today, what am I talking about today? We're sort of continuing on where we left off last time, and I thought that would be good since no one really had a lot of time to prepare. And we're presenting today, or I'm talking about, Oblivious Transfer, the Oblivious Transfer extension, but for malicious adversaries. This is just an overview or a bit of a reminder of you know, what we're doing today compared to with last time. So last time we looked at, you know, semi-honest adversaries. Today we look at so malicious adversaries with abort, meaning that if the malicious adversary gets caught, we can we abort the protocol. So we can't you know, force it to go to an end. And a reminder, what do we mean by OT extension? OT stands for Oblivious Transfer. And the idea behind most, if not all, OT extension protocols is to use a small number of so-called base OTs. And these base OTs use this expensive asymmetric encryption to transfer some keys. And using these keys that we transfer, we can run a large number of extension OTs with cheap symmetric encryption. And that's the key idea, which we talked about last week. And this is just a notation of what we're doing today. We're saying we're doing L times OTM. The L stands for the L stands for the number of values we are transmitting. I see I have a typo here, but I'll continue. So the number of values we're sending, and the M stands for the length in bits of the values. And here the M should be L in this case. But you have to just ignore that.
I see.
All right. Okay, so let's do a recap of last week. Last week's protocol. So we looked at this IKNP03 protocol, and here I'm just highlighting. Let's just remember a bit what the protocol is, but also showing what are the differences of how I'm showing it today. Like, how will it look different today to last week? And in the paper that we have for this week, they describe this protocol, but they also use a pseudo-random number generator. And why is the pseudo-random number generator used? It's just for optimizing the protocol a bit. Instead of transmitting these, last week we had these, you know, two matrices, if you remember, matrix T and U, with size M by K. And this week, instead, we're only transmitting keys to this pseudo-random number generator, and the keys have size K, and we can expand them to size M. So we're sort of just optimizing a bit. And one other difference is here we sort of define the T and U matrices somewhat different, but in the end, we end up with the same. So essentially, it's the same protocol, but just a slightly different take on it that they describe here. And well, it's easier to see in like a graphical form, at least what messages are exchanged. I don't want to dive too deep into this because we had it last week, but it's good. It's a good reminder. So we start at the first step. The sender chooses this S, and the receiver chooses, these random Ks. And then we use the base OTs, and the sender sends most these pairs of these Ks with the base OT, and the receiver receives whatever SJ the receiver chooses to receive. That's the first step, and then in second step, the receiver computes these UIs here, which are the columns of the U matrix, and sends them to S. And the sender receives these UIs and computes the Q matrix of these UIs. Then does some more computation here to compute these Ys and sends them over to the receiver, and then the receiver can decrypt the Ys to the correct Y to get the correct X value. So that's what we looked at last week. But this week we're looking at malicious adversaries. So the question is,
can you spend a bit more on this slide? I mean, I know it was last week, but using a slightly different formalism, and yeah, I think I didn't catch it now.
All right. Yeah.
So step by step, what happens is that in the first part, the sender is actually receiving something, right?
Exactly. So the sender receives these Ks.
Also, is this is what's on this slide? Is it with these modifications already, or is it exactly as it used to be last week? On the last slide, you showed several modifications. So are they already here?
These are, yeah, they're in here.
Okay.
Oh no, wait. Yes, they are. They are. So we're using the PRG, the number generator G, and these Ks are also only K long. Essentially, how does it compare to last week's? I have to change my sound as well.
The K is the security parameter, right? That's like
yeah. But so last week these Ks here, the security parameter would be kappa, maybe, so we don't confuse the two. Okay. And these, but these Ks are
K is not kappa. It's a different parameter.
It has to be different, right?
No, well, the parameter is kappa, but these the K matrix or the K matrices are not kappa, right?
Okay.
Okay, I see how this got confusing.
Yeah.
That's
the
my
K
bad
and
to use
got
K
confused.
twice.
Yeah.
So the one in exponent is kappa, and the K are
exactly.
Just,
this is
vectors.
Yeah, these are vectors
Elements
now
of
flanked
matrix.
kappa.
Yeah. Okay.
I'll have to, yeah.
No worries. This thing
exactly,
is not
but
so much confusing.
Well, you have to. The way you can think of it is, so you can replace the Ks here with the what's it?
Any element.
With the T and U matrix. In last week we had right. Let me see.
So essentially, these are like seeds for randomness to generate the columns of the matrix.
Exactly. Yeah.
If you remember
Okay.
last time, then the columns were quite long, while the rows were
like
short.
the length of million or something. Like
exactly.
Yes.
They were I wonder if I have this.
Yeah, I taken a screenshot. If you want, I can send it to you. It's TU and K.
Yeah. Wait. Oh. Wonderful. Does that work? So this was, I think, last week. It would look somewhat like this. So we would choose T and U and transmit the T and U matrix. instead.
Okay, so now like coming back to the current slide, what we do is we choose at random this case, and then we get them through some kind of a pseudo randomness generator. The case, where does it happen? Oh, okay, 2A.
Yeah, exactly. Here we I mean, this differs slightly. So T and U are, whereas here on last week we looked at it. So T, X, or U, each row would be this a repeated random bit, right? Whereas well, these are columns now.
Yeah.
But yeah, I mean, it's sort of. Yeah.
So okay, but the step 1B, let's go it through it step by step. So at 1B, for every j from 1 to kappa, I guess, not k, there is one thing sent through the OT. So the sender receives it. And then we go to, so the sender actually receives a vector of length kappa, and it consists of k0s or k1s, depending on sender's choice. And then at point 2A, what happens here?
Yeah. So the I mean, what here the receiver now creates two matrices, P and U. Okay, and the P matrix we just computed like this, and the U matrix we compute like this, and these are the columns now in the U matrix.
And what is the size of this matrix? I mean, this G, it goes into matrix of size kappa times M, where M is enormous.
Well, the matrix is M times kappa. So G expands K length key to M bits, right? So so that's we define it here, but yeah. So we expand it to length M, and the U matrix is M by K, and the T matrix is M by K. So again, we have the T and U matrix, and but just slightly.
Okay.
And yeah, so the difference now is that we're just sending the U matrix in its whole to the sender. Yeah.
Okay.
And sender can then compute the Q matrix again, size M by K, M by kappa, sorry, by doing this. And SI is here just a single bit, similarly to last time, just a single bit multiplied by.
And it's the same bit that was used before in this first Oblivious transfer, right? No. This slide.
Oh yeah, up here. Yeah. So
it's the same.
Exactly. So that's part of. Yeah, and then exactly that way we can. If you, I mean, I sort of, you have to write it out, and then you can see that it's correct. But it's not really as intuitive as what we had last week. But if you.
But what's the property of Q that we are aiming for? So if S is 0, for example, then receiver got K0, and
yeah.
Oh, if S is 0, then receiver got K0, so it's gonna probably cancel out with G to KI SI in this and to be in the last.
Exactly. Yeah.
Is going to cancel out, and he's gonna be just left with UI. I think.
It's slightly confusing.
No, yeah.
Last week, the diagram was slightly better, at least for me. Okay, so seeing matrices as matrices helps to visualize in head as an idiot.
Yeah, this is a bit more tricky.
Yeah,
I mean, essentially it's the same as we had last week.
yeah.
Okay.
I am just looking at
I'm
the
not
picture
so sure
while
it's
I'm
the
talking.
same. So
yeah, I'm confused as well.
So last week there was this property that UI XOR TI was equal to R. So like if you took any pair of columns, column I from the T matrix, column I from the U matrix,
from the U matrix,
together you got R.
Yeah.
Last time, and in this variant, I don't think it's true.
Yeah. So I am looking at the slides from last week. What he said is true. Yeah, S is an element of 0 to 1 cover. Q, 46 Q. Yeah, I'm not sure. I'm confused.
Okay, so I think. Okay. So the Q, did we have this Q last week as well?
I doubt it.
Yeah, here you receive the Qs.
Yeah, yes.
Those are the ones you receive. Instead, you receive the column Q. That was that's the difference now.
But you receive it directly. You don't compute it based on.
Yeah, exactly.
Something.
And now we have to compute it. But in the end, we have like this expression here is true in the new version as well. The jth row of Q is Rj times S XOR Pj. And that was true last week as well.
So can you go to this next slide? Maybe we can parse it like together and see what actually happens here. So this Q, I mean, yeah, this Q, I mean, it should have some nice property, and maybe we can just go through the two cases here, which are S equal 0 and 1. So for S equal 0, I guess the first part 0 times U is 0, and you're gonna just get G from K. It's the same S, right? So so K
0, yeah. So GK
I0. GK I0, and for S equal 1, you're gonna get UI and G of KI1. And UI is okay, and so UI actually have a G a KI1 inside, so this part is going to cancel out. So for S equal 1, you're gonna get G KI0 plus R. So this is the only difference. So QI equals either GK0 or GK0 plus R, depending on the choice of S.
Yeah. So what do you say? So UI.
Yeah. For S1, it's UI plus R. It's yeah. And
no, it's not only. Oh yeah, sorry, yeah.
Yes, because there is this factor GKI1, but it cancels out with because you
right. So this
you explicitly add it.
And when was 0, it was just G
KI0 without
0. Okay.
And not obfuscated.
Then how does it continue? So J, we just take QJ and compute these two. Okay.
Wait. So what's H here? I don't remember.
H is a hash function.
Okay, just a hash function.
So S equals 0. Now let's see.
And Y, I mean, X's are, I assume X's are the inputs that we want to actually use in the Oblivious transfer that we are preparing for, right?
Yeah, these are the ones we're sending. So
okay, yeah, and Y is defined here.
Yeah, I feel like maybe I should have prepared this, but well, let's see how we get this. So okay, so I'll break up as the Y's for the two cases as well. Sorry, Y0. And then let's see what happens on the receiving side. Right. So here we say, just get that, and then.
And you're just sending it here. I mean, like the
now we're just sending
Y0 and Y1. You are just sending it, not with Oblivious transfer, just like directly.
Yeah, just plain text.
Okay.
Plain text, and then because. Yeah,
I mean, it's
encrypted through this receiver, and the receiver has so he has the HJ TJ because we computed the TJs up here, right? And let's assume that we received S0. Maybe let's say R. I think R has to be either 0, 1. Let's see what happens if we have this. So A Y0. Y0. I'll just write X instead of XOR. If that's okay. Okay, what's this now? We replace it with this, I suppose. The Y0 and then X, this part. Replace that. Oh, whoops. Maybe that wasn't so wise. Sorry about that. I'll make some space. Okay. And TJ, so what's TJ? TJ is this, right? So we replace TJ with its value that we defined it with up here. And so these two cancel out, right? So we end up with X0.
I'm still on the left side, and I just ended parsing the left side. So like it occurs that the string inside of the hash is stored with either S or R or both S and R, depending on the choice of S and whether you look at Y0 and Y1. I think, like, so depending on sometimes you are adding S here, depending on which Y are you looking at, and also Q. Sometimes it's with additional obfuscation of R or XORed with R, and sometimes without. So there are like 4 options here, I guess. And
yeah. I mean, here there are two. Yeah, I suppose. I mean, I don't know, I have bad sound right now. Someone's
okay,
mowing
so
the lawn outside. I'm sorry.
Now I think like the last step. So the receiver receiving this y0 and y1, and he would like to make a choice which one of them he actually wants to recover, and how to how to make the choice, which bit tells us about the choice of the receiver. Is it R?
Sorry, I'm going to change headphones.
Okay.
I'll get this is in a minute. All right.
Okay, so I think what we need to know, I mean, and I don't see it just yet, is that h of jt equals either h of jq or h of jq plus s.
Yeah. So you okay.
But S is not variable anymore. It was chosen in 1B by sender for obfuscating which key he will use for sending the final YA.
Yeah, and what's weird is that S might actually equal 0. In that case, the same hash was used for x0 and x1.
I think this is the S here is the vector S.
Yes, it's the vector.
So
yeah. But if it's a vector,
no, SI is a single bit.
Yeah, that should be SJ here, I guess, right? You are like you have got QJ, so there should be SJ.
Where are we looking now?
One line.
Here.
No.
This line, no?
2D, second line of 2D. Yeah. So there is QJ, and I suppose it should be SJ. At least I.
No, I think this is not a SJ. This is
QJ is a vector. J. Yeah,
QJ is a vector. Oh, damn.
But let's see what happens when for y equals 1. Maybe should we look at that case because we have or the y1 case rather. So what? Now I'm confused. Okay, I'll continue. I'm gonna have to demolish my slides a bit to make some space. All right. So for S0, but I think S1 is probably your start with S0 and Y1. Okay, so what is Y1? X.
So, like, what does it mean S0? Like, just a second ago, we said that S is a vector.
So the thing is, S is a row, and so in this notation, if you have a lower index, it's a row, and if you have an
upper
and
index.
if you have
is a
an
column.
upper index, it's a column.
All right.
Or
So
in most of the places, actually, now I don't think it's consistent, but.
So
yeah.
what does it mean S equals 0 if it's a row?
I think it's so the S we had up here. So I guess if S is 0, then the QI at SI is 0 for QI. So that's what we mean. Maybe I'll write SI. That should be.
So the whole row is 0, like.
Yeah. Or the column, and these are columns. The whole column is only this value. Y1 is then paste. QJ, I'll replace, because now we have to think about what QJ is. It's getting a bit messy with indexing, but I'll copy from.
But still, so what does it mean SI equals 0? It means that it's a row full of zeros, or it's just a value?
See, it's a column. Also, so here, when we use
generally, when we chose random S at 1A, we chose it as we chose it as a matrix, square matrix, or not?
No, S we choose as
it's one row.
S is
we chose just one vector, right? So all right, so S is a vector, which means that SI is a value, and I mean there is no right, like SI is always just a value since S is a vector. Okay.
Yeah.
So coming back to my kind of original question, so the second line in 2D, do we really mean adding the whole S vector here, or should it be the jth position in this vector?
QJ here is a row. So S.
Okay, QJ is a row. So S needs to be a row. Okay.
Yeah.
Yeah. I'll continue trying to break this up. I guess if S is 0, then Y1 is this. We would transmit it. I'll remove this. The next J is string. So if the R is 1 as well, we would replace it with Y1. And what do we have here? So I guess when R is 1, what did we say? TJ, base TJ. this. Nope, these are rows. Yeah, okay, now I'm lost as well.
So still, we need somehow to get this property that tj equals either qj or qj plus s. So one of them will cancel out. And the receiver will get either.
Yeah, I mean, somewhat similar. Let's look on the original slides, maybe, or I mean, the original protocol. Maybe it's clear from here. So I mean, they do cancel out. So what happens? You qi, qj, you can replace with this thing here. So if r is 1, rj is 1, we can replace qj with s xor tj. So s xor tj xor s is h of j comma tj. So if we replace this, and if rj is 0, we would replace, or then qj would be simply 0 times s tj. So we would also have hj comma tj. So either way, we can just XOR with hj tj. Yeah, so it's a similar trick, but I also think it's not as intuitive. But,
and the overall cost of this protocol is roughly the same as the other one.
yes. Should we stay on this, or?
No, I think we can continue.
I think personally, I have to reread this paper as well.
Yeah, but I mean, it's one thing to get all of these computations to the point, and the other to understand roughly what's the gain and what is a potential trade-off here.
Yes. Yeah, but it is sort of a derivation of last week's, just with some trying to bake into the idea of using a random number generator, just to make this matrix a bit smaller. All right, so I was going to ask the question: why is this not secure against?
So this one is still not secure.
No, this is the last week's protocol for semi-honest. And I don't know if I can roll back to the slide as it was. Looks good. And I'll leave it as an open question. Why, or oops, how can a malicious adversary break this protocol, right? So what if the sender is malicious? What could the sender do in this case? So again, I think it's somewhat of a definitional question, like we discussed last week, where you know, what does security mean in this case? If the sender is honest, the sender can still control the output of the receiving party by, you know, simply choosing pairs as the same values. So the sender can also, you know, control what the party receives at the end.
If the output is not public, but it stays with the receiver, I don't think that the sender can learn much from this protocol, even while being malicious.
Exactly. So in the paper, they also say that sender can be malicious and the protocol is still secure.
Mm-hmm.
I guess what to think of, how to think of it is the sender only really sends one message here.
Yeah, and he doesn't receive anything, so it's
yes.
hard to imagine that he can learn something without receiving a message.
Yeah. On the receiving side, or the receiver, there's I'm gonna speed through the slides a bit.
So probably he can lie in 2A, computing something different and well prepared,
exactly,
right?
Yeah. Yes. So the receiver could, I suppose he could, because the sender only has one of these two values. It's one insight, but the way, what we need to stop is the receiver from lying about which R value it used, or rather the receiver in this case could use a different R value. This is a vector, so a different R vector for each of the UIs. That's what we need to stop or check, that the receiver always uses the same R vector when computing these UIs. And what could happen is, well, if the receiver can choose different R's here, he could in the end learn things about the selection, the S vector from sending party.
Could we take a look how that would happen? Because in the text it only states that it is so, but I couldn't
figure it out. I was hoping maybe someone knew. So yeah, I'm not sure. Anyways, that's what we have to stop. It doesn't say it in the paper.
The one thing is that how to cheat by changing R, but what's actually more interesting for me is how, I mean, why is it the only way he can cheat? I mean, why the only thing we need to do is to prohibit him from using different R's? Why some other arbitrary modifications are not dangerous? Like, for example,
I suppose at this point, the receiver knows nothing, yes? Because from the previous step, he knows nothing. Because
also, I guess any modification he does can be translated in a modification of R, because the only thing he actually sends to the sender is UI. So if he sends like different UIs than he should, any change can be translated into modification of R's.
That's true. That's possible.
I think that's yeah. I think that's it. And now, well, the questions how to cheat is probably pretty complex. But what's actually the minimal interesting part is whether prohibiting him from using different R's is enough, and it looks like it's enough, because then he will not be able to send anything else but the thing which is stated here.
Exactly. Yeah, so
So
you
how does
put
it,
it well.
does it happen with some kind of a commitment scheme or something?
Yeah. So to frame the problem, the receiver, no, so the sender sends these two different UIs, and the receiver has to verify that based on the UIs received, that they both use the same R. So that's sort of the problem we have to solve.
Okay. So those are just two instances of many that we
exactly, but we have to yes. So if you want to verify that the receiver, or I mean the sender, learns nothing, you sort of, or I'll get to it in a moment. So my point is, we can do it for all the pairs, but then we would have L squared pairs. They also talk about an optimization where you only have to do for a subset of all the pairs, I and J, to verify that the sender doesn't cheat. I mean the receiver. Sorry. Yeah, and it's a sort of a commitment scheme. This is the exhaustive one for all the pairs. Just the receiver creates these values and sends them to the sender. The sender checks the values, exactly checks of the qualities, and then if none of them fail, then it's okay. But if one of these fail, these checks, then the sender aborts and it just aborts execution.
But do we need to do it for every pair of rows, or how?
So this is for every pair of with the security parameter is L, which is kappa plus P in the paper. But so and we do it for every pair. And what is a pair? A pair, I guess, is two rows.
Yeah, I mean, not for every pair, probably. If we know that the first row is using the same R as the second, and the second is using the same R as the third, then, well, we don't really need to check whether the first one and the third one are using the same. So we just need to do it kappa times, I guess, not kappa square times.
Not so sure.
No, I think this is kappa
check
square.
will be like we'll have perfect correctness, and that's why you need to do pairs, all pairs probably. Like,
what do you mean by not perfect correctness?
So maybe the check will fail with some probability, and that's why you need to.
Okay.
But I'm not sure about that. I mean, it can give you false positives, maybe like
Yes. So
like
one a check fails with, or rather, the receiver can learn one bit of information about S with probability 1/2. So that's why we repeat the checks. In this case, exhaustively, and we can ensure that the receiver only learns P bits about our secret S with probability 1 over 2, or 1 divided by 2 to the power of P. So, but for every time the receiver tries to fool us with one pair, he can fool us with probability 1/2. And the way the receiver can trick us is or learn is he can put in wrong values, and he can the receiver can learn if the verification doesn't fail. The receiver learns that can learn something about which S bits we had for alpha and beta. So here we have S alpha, S beta, and depending on which S alpha and S beta we have, the check might fail or might not fail. So the receiver can learn something about it from there. But it's well explained in the paper on page 11.
Mm-hmm.
Yeah, so we just insert it pretty much, and then it works. I think I'll just go through the performance and then we can start again. But I like this paper. Had a nice table on the performance. So I highlight two rows here. We have like the last week's protocol for the semi-honest security model, and we have this week's for the malicious security model.
What does it mean covered? I mean, it's like intermediary between passive and active.
Covert is was it that someone can get caught with a certain probability or so, or rather.
So he can learn something, but then he'll get caught, or? Yeah,
or like maybe exactly. There's a probability that the malicious person might learn something, get caught if he tries to cheat.
The most surprising thing on this in this table is that they have different communication depending on the fact whether it's LAN or WAN. I mean, local and cloud. they send like different size messages. What? How is that possible?
I'll get to that. I mean, it's a long paper, I'd say, so many aspects talked about. The reason why local and cloud differ here is because you can optimize the protocol by changing the parameters of it. So you can either increase the number of base OTs, and by doing that, you can allow yourself to decrease the number of checks you do in this commitment scheme. And the other way around, you can decrease the number of base OTs that you require, but you would have to increase the number of checks you perform. So I guess if you go one direction, you have maybe more computation and less communication, which is in the cloud scenario might be better, versus locally you might want to have more communication heavy and less computation heavy to increase the speed. And they divide it up nicely here. You see the runtime of the base OTs for last week's protocol, roughly 23 seconds. That's for, I think, 128 instances of a base OT. And because our matrix is a bit larger, it takes a bit longer for this week's. So it takes roughly 0.7 seconds. And we also have a few more base OTs to execute. But it's actually pretty, I mean, surprisingly comparative, or like comparatively fast when you compare it to the semi-honest model, which is it's only it seems to be a constant factor added on, which is usually not the case. So yeah.
So it would be nice to like have some intuition how many OTs are like, I don't know, enough to compute something actually meaningful.
Yeah, they have it in the just in the paper. They had some really nice numbers just in the start. Scroll. Okay, so here, example 1.
Yeah, but that's what I meant actually.
Yeah, so for the even AES, that would take around 10,000 AND gates.
It would compute like ages, 2 to the power of 19 OTs.
Yeah, so 2 to the power of 19, what's that, 500,000. Yeah. Am I wrong?
Oh, but no, it's actually
per second then.
That would probably take like less than a second in the local scenario, right?
Yeah, so seems like it's only a microsecond, 1.3 microseconds per transfer.
But this number of OTs are like, is it assuming that 2 parties are computing it?
I would assume for this example, I would assume so.
Okay.
And for the GMW, what did we have? We had 10,000 AND gates, and then for every AND gate, we need 1 OT, right? Or we needed n squared OTs, I think. But if we have 2 parties, we need maybe like 4 OTs or so, 5 OTs. It should be. I mean, should be feasible. Depends on how often you need to execute it. So. Yeah. Anyways, that's the presentation. But I don't know. A lot of open questions still about the protocol. My side and from your side as well.
Okay, thanks a lot. I guess it would be nice to eventually, I don't know, discuss some table which would actually